can start. The topic is about MHD simulations. And the first question is anybody of you doing MHD simulations? Oh, so actually you should be standing here instead of me and giving this lecture, because I'm not really an expert in MHD. I tried to understand this a little. I still don't understand. So if I say something incorrect, please correct me immediately. Or if you have really comments, please do comment, because I always try to avoid magnetic field. On the other hand, it's difficult to avoid magnetic field in the case of accretion flow. So, okay, let's start. So magnetic field is actually everywhere, inside and outside different bodies. Here I list some values of the magnetic field strength. Here I use Gauss as a unit, but I understand that in SI system, Tesla is formally used, right? Maybe. Anyway, I think most astronomers still use Gauss. So here there are some numbers. In the case of Earth, the intensity of magnetic field is 1 Gauss. In the case of Sun, the intensity is from 1 Gauss to 1000 Gauss, depending where you measure it. And we will return slightly to this issue at the very end of the lecture. So this regular field is weak, but if you look into some sunspot regions, then you can measure this very high magnetic field intensity. Of course, there are sources which possess much higher magnetic fields. Neutron stars in low mass X-ray binaries, they have something like 10 to 9 Gauss, and this is considered to be a very low intensity magnetic field in comparison with effects related to gravity. On the other hand, for pulsars, 10 to 12 Gauss is the typical value, and then the magnetic field really determines what happens close to the star. Magnetars, they have 10 to 15. So you see that the range is quite large. But the magnetic field is present also in low density medium, like interstellar medium. It may not seem spectacular because this interstellar medium has intensity 10 to minus 5 Gauss, and intergalactic medium 10 to minus 9 Gauss. So it may seem unimportant. On the other hand, in the case of the Sun, magnetic field of the Sun does not have an important impact if you consider the amount of energy contained in magnetic field. On the other hand, if you look at low density media, like, for example, interstellar medium in our galaxy, then you will notice something like this. The magnetic field energy density is more or less equal to the cosmic ray energy density. That means non-thermal particles. And then if you compare it with thermal gas, hot or cold, does not matter. Again, the energy density is comparable. So you have equipartition, in that case, between different forms of energy. I'm not sure if there is any official explanation of that. This is just an observational fact for sure. For the explanation, I don't know. in general, the origin of the magnetic field is still under discussion, because we can use always the dynamo to create stronger magnetic field if we have weaker magnetic field. But if we have no magnetic field, then we cannot easily create something out of nothing. So this is still the primordial origin of magnetic field, which is quite intense in this sense. It's I think not fully explained. Of course, if you have a lot of magnetic field in the interstellar medium, then you can always create magnetic field inside the star, because when you form the star through the collapse, then you intensify, you drag field lines and you intensify magnetic field. Since the lecture is basically about accretion flows, then we should spend a minute on possible role of the magnetic field. And it's incredibly important, despite the fact that I didn't discuss this so far. This is sort of a list where the magnetic field plays absolutely a key role in accretion process. First, I mentioned already in the lecture 4 that if we want to use hydrodynamical approach, we actually need to postulate certain presence of the magnetic field. Otherwise, the mean-free path of particles is far too large to use hydro approximation. It is also, magnetic field is also responsible for alpha viscosity in accretion flow, and we developed the the theory of alpha disks of Shakura-Sunyaev, and we will discuss this alpha viscosity more in a minute. In the sources like polars or X-ray pulsars, which have large magnetic field, then this magnetic field determines how the accretion proceeds. We talked about column accretion from time to time already during the previous lectures. So you need strong magnetic field to force the matter to follow the column accretion. Magnetar phenomenon, collimated jets, they cannot be explained without magnetic field. Compact corona also must be somehow related to the presence of magnetic fields. Any actually X-ray emission is related to the presence of magnetic field. Collimated winds, whatever. So we need that continuously. So why we didn't use it before? Because it's difficult. That's the only explanation. So the easy part is some summary of a school course about the magnetic field, including Maxwell equations, which will appear soon, and then everything becomes enormously complicated. So school summary is simple. We have electric field and magnetic field. In the case of electric field, we have charges. Charge can be positive or negative, and then we have field lines. In the case of magnetic field, we do not have this kind of geometry, right? Because we have no magnetic field monopoles. On the other hand, otherwise, apart from magnetic field charge, there is nothing like that. Then electric field and magnetic field are kind of equivalent, because if you change the reference system, then you can change, for an observer, you can change electric field into magnetic field, or the other way around. Because going from one reference frame to another, if in the rest frame of an electron, you do not see the magnetic field, right? You have to change the reference frame to see the magnetic field. But if the electron moves, then of course external observer will measure the magnetic field, and if you have electric current, you have this explanation how the magnetic field forms around a current. When we discuss cosmic plasma, we rarely refer to electric field. Occasionally, yes, in the case of pulsars and emission mechanism, we do consider electric field directly. But normally, we consider that plasma is neutral, so we have no charges on average. Still, we have magnetic fields, right? As I showed on the previous slide. So we do some kind of cheating, in a sense. And formally, magnetic field, we say that magnetic field does not perform work because acceleration is perpendicular to the direction of the field. On the other hand, in astronomy, so this is what we say at school, in astronomy, we say that in cosmic plasma, the particles, either particles follow the field lines, so they move along the field lines, not perpendicularly, or the field lines are frozen into the plasma. It apparently looks like contradictory statements. But this will be explained soon. This is fortunately the easy part. So how we are sure that we see magnetic field? Well, first of all, it is observed directly in the data when we see polarized emission. Polarized emission is usually the signature of the presence of magnetic field, and from the way how the polarization vector is aligned, you can determine what the magnetic field is doing. Here you have two examples. Well, this is more or less the whole galaxy. So the whole galaxy is full of magnetic field, like Milky Way. Here, this is just the nucleus, and you see some kind of, well, almost like a jet, but it's radio quiet. I think it's a Super-2 galaxy. So this is really the nuclear part of the galaxy. And the emission, which is measured on those images, is polarized synchrotron emission. So this is simple explanation of both synchrotron radiation and the apparent contradiction between the statement that plasma moves along the field lines and the statement that electron moves perpendicularly to the field lines. What if we have a magnetic field line and this is the electron is moving along such a spiral. So in a sense, it's moving perpendicularly to the magnetic field, but it's drifting along. So from the point of view of synchrotron emission, this gyration, or how to say, this is important because that leads to synchrotron radiation. But from the macroscopic point of view, the electron goes along the field line. And this is the statement used in MHD approximation. So at least this is easy to understand. Now Maxwell equations. So there are 4 equations, and Maxwell was responsible actually for putting them together. In physics, there are ways to write all those equations in a compact form of a single equation, but for us, it's more interesting to see them separately, because then you see what the different parts are doing. So this means divergence, this is rotation, so electric field and magnetic field, those are vectors. You see the symmetry. So here you have electric field, magnetic field, electric field, magnetic field. Structure is similar. On the other hand, here this divergence is related to the source of the electric field, which is the charge. In the case of magnetic field, we have 0 because we have no magnetic charges. Magnetic monopole would have to be here. And here we have an equation which determines the change of the electric field in time. And we see here the presence of electric current, so the stream of charges. In the case of here, magnetic field, we have only time derivative, but we don't have the current because there is no current of magnetic charges. Otherwise, the symmetry is perfect. By the way, here there are different notations, and in some notations he appears, in some notations 4 pi appears, in some notation this epsilon appears, the electric constant, and mu whatever. So pay attention to units. I'm not sure finally. This is, I think, in SE units for a change, because I copied this from this lecture. So be careful, 4 pi can also disappear or reappear, as in the case of radiative transfer. But what is here important is that the magnetic field can change in time if something happens, or, well, due to the presence of electric field, right? Still, when we discuss the Dynamo equation, we have only equation which includes only magnetic field. And then we somehow say that magnetic field multiplies. But it's important to remember that electric field is somewhere in between. And this writing the equation only for magnetic field change is possible because we have all those other equations at our disposal. So sometimes it's more easy to understand Maxwell equations when integral version is used. I'm not sure what would be easier for you. If you want to look at it, this is just taken from Wikipedia, and Wikipedia actually nicely explains that, well, what is the meaning of the divergence. So you can calculate the volume content of the electric charge, and then the magnetic field is calculated at the surface which goes around this volume, etc. So I'm not going to concentrate on this much. You can look in any textbook for that. Anyway, as you see, changing electric field induces magnetic field, and changing magnetic field induces electric field. So they are both coupled. So now, how we derive the Dynamo equation, which contains only magnetic field? How this miracle happens? Well, at some expense. So to get this equation, we have to drop this term in Ampere's law. So only current will remain. In a moment, we will show what underlies the assumption of dropping this term. So we somehow break actually the symmetry, right? And then anyway, to calculate, to solve this set of equations, we have to supplement this set of equations with the Ohm law, which describes the properties of the medium. So for the medium at rest, we have a connection between the current and the electric field, with sigma here being the conductivity. But this is for a medium at rest. We'll return to this issue in a moment, but first let's try to see how it's possible to neglect this term. Here we do in a similar way as we did for the accretion disk equations. You do just dimensional analysis, right? You have full equation, for example, like this. So this means gradient. Gradient means electric field divided by length, right? Because this is the differentiation. This is differentiation in time, so this is magnetic field divided by time. And then we can calculate electric field from that. It's not solving equation, of course, it's kind of cheating. Then we take the second equation, and we do the same here. So this is the magnetic field divided by length, because this is differentiation in space. And then we estimate this term, right? This is electric field divided by time, and we have here 1/c squared. And then we use also this equation. So instead of electric field, we put here magnetic field and additional L divided by T. So we have here this and this. And now we calculated the ratio of that one term to that term, right? What we get is 1/c squared and then length divided by T squared. So the interpretation of neglecting this term is that we assume that changes in the system are much slower than the light travel time across the system. This is this assumption underlying the Dynamo equation. If something happens fast, then this Dynamo approximation is not appropriate. So Dynamo equation will describe slow evolution. And then indeed we can drop this term. Then one more modification, because we are usually interested in a medium which is moving, oh, sorry for the misprint, moving with some velocity. So in a close analog to Lorentz force, if at the rest frame we have just this term, we have to add this term related to the velocity to get the relation between the current and the electric field in the medium. And now we are ready to derive the Dynamo equation. It's quite a formal derivation, like we did those exercises for in the case of deriving the motion of the test particle around black hole. You just must know that you start from this equation, and then you have to calculate the rotation of this equation. Current is a vector. And first you have to derive it by this, divide this equation by sigma, because it's convenient. So then you have rotation of electric field, and then this rotation of U times rotation of V. And then you can use Maxwell equations to derive this thing. So this will give this will give this. If you look carefully, it's not very complicated. It's kind of mathematics. But you will see that here this time derivative of the magnetic field will appear. And here you can remove J by using rotation of B. And then you rearrange equation to get this, right? So then finally, this is the dynamo equation where you got rid of the electric field. So it does not mean that there is no electric field. It means that you just eliminated this from the equation. And you usually don't return to it anymore because it's not needed. Here there is one more coefficient, magnetic diffusivity, it's difficult word, which appears, which depends on those two previous quantities. And normally it remains here under the differentiation. On the other hand, if you assume that it's constant, and usually we assume it's constant, then this comes in front and the equation looks simpler, and this is the usual standard dynamo equation. So then you have really magnetic field evolution and not the no electric field. On the other hand, you see here immediately that if you start with no magnetic field, so B is equal 0, then time derivative of B is equal 0, and you cannot generate something out of nothing. But let's discuss those two terms, the meaning of those two terms. So the second term, it is the second order space derivative. So we had something like that when we discussed the time evolution of an accretion disk, right? We had a diffusion term when the initially concentrated material was slowly spreading. It works exactly the same. So if there is no motion of plasma, so this term vanishes, we are at the rest frame, what the magnetic field can do is just to diffuse. So the intensity of the magnetic field decreases, decreases, and decreases, and decreases. And that's it. On the other hand, there can be another limit where you assume that conduction, that we have a perfect conductor. So this term is equal 0. And this term is responsible for multiplication of the magnetic field. But at the same time, this term means that magnetic field is actually frozen into the plasma. And this is the most efficient multiplication of the magnetic field you can have. Usually you have a counter reaction of those two terms. This is this generation term, and this is this diffusion or decay term. And to characterize the relative ratio of those two terms, people use dimensionless magnetic Reynolds number, which using more or less dimensional quantities, here you need to have length, here is the mean velocity, and here is this value eta, and then you can decide whether you can neglect one of those terms or you have to keep both terms and calculate everything properly. So there is one absolutely basic achievement of the dynamo theory in the context of accretion disks, and this is the explanation of alpha viscosity. That was done much later than the paper Shakura-Sunyaev, because Shakura-Sunyaev disk paper was published in '73, while this explanation of the nature of the viscosity was published by Balbus and Hawley 1991. The paper is now cited more than 3,000 times. And this is really a very important achievement, because earlier Shakura and Sunyaev, they had some intuition that this turbulence or viscosity should be somehow related to the magnetic field. Those people, they showed how it is related. They solved the set of MHT equations, which look like this. So this is the continuity equation, something which we had before in the context of accretion disk. Those are vectors, of course. Here is the equation of motion. We also had such an equation of motion. Here is the gravity or the gradient of the gravitational potential. Here is the gradient of the pressure. We also had this term before, but you have additional terms. You have the magnetic pressure here additionally, and then you have the Lorentz force. And then you have this key dynamo equation in this form. So you see, we dropped, if I can go back to this, we dropped this term, no diffusion term, just amplification. Why they did that? They did that because they actually wanted to solve everything analytically, and they did. And the enormous success of this paper relies on the fact that they actually did everything analytically. Of course, it was not time-dependent, full analytical solution. That would be too much of a luck. But they used linear perturbation theory, and they showed that this system of equations leads to unstable solution, to rapid multiplication of the magnetic field, more or less in the dynamical time scale. So you start with a differential rotation, that was the setup, more or less Keplerian disk differential rotation, and then the magnetic field present initially multiplies. So when they published this solution, they actually didn't know that this instability was known before. So at the beginning, people started sometimes to refer to this instability as bulbous-Hole instability. Later, somebody noticed that it was determined before by Russian Velikov and even Chandrasekhar, but in different contexts, right? People didn't realize it's important for accretion tests. So now official name is magnetorotational instability, but still bulbous and Hole should be cited in this context when we discuss accretion disk, because this is what they really noticed, and this is of key importance. Because now, instead of hand waving that we have some kind of alpha viscosity, whatever, we have a physical mechanism. So this physical mechanism is kind of easy to understand intuitively. If you have two, let's say, blocks of material inside the disk, and there is a magnetic field line like this, then if you perturb this position of one block and the other, then they are still trying to remain along the magnetic field line, but the magnetic field line is now stretched. So those two parcels start to interact. On the other hand, rotational differential rotation takes those two particles apart, because from the top view, you see the following. Here they start at the same radius, and now this blue one, let's say, is closer to the center, right? So its differential rotation velocity is faster. This one is lagging. So that one is dragging that one, while that one is halting this one. They finally exchange the angular momentum a bit. And this is why this mechanism provides the way how the angular momentum is transferred outward. Because that one tries to pull this lagging one. So somehow accelerates. Of course, it cannot lead to infinite strength of magnetic field, whatever. It actually leads to a turbulence, but this turbulence is doing what I'm saying. It's responsible for the transport of angular momentum outwards, but the presence of differential rotation is important. If you don't have differential rotation, this would not work.
So if you want to understand in terms of conservation of energy, so when the magnetic field amplifies, what happens to like the kinetic energy loses?
Yes. Yes, and then accretion additionally happens, right? So it is all at the expense finally of the gravitational potential energy. So a few years later, results were published because, you know, linear analysis is not fully satisfactory. People want to see how the saturation of this situation will look like. So it was published a few years later, first 3D numerical solution. And what they used in this case to save a lot of computing time, this is so-called shearing box approach. This is still frequently done in the context of accretion flow. This is the formal representation of the shearing box conditions, but it means that you take only a small box inside the flow of the length Lx, Ly, and Lz. And then you assume that everything repeats. So the all function at x is the same as function at x plus large Lx. So you use kind of periodic conditions. So in this way, you mimic that your parcel of the gas is part of the large global flow, but it's cheating. Of course, it's not global solution. There is no real accretion in this system. But you can see the dynamics. You can see multiplication of magnetic field. But it is very, very limited approximation. On the other hand, 3D time-dependent MHD calculations are very time-demanding because you have to do time computations resolving dynamical timescales. When I discussed time evolution of accretion disk in thermal and viscous timescale, I referred to some codes, but they were mostly not 3D, but 1D. And then they required computing only the evolution in thermal and viscous timescale. Because I was assuming then hydrostatic equilibrium. Here you have to resolve much thinner, faster dynamical timescale. So then, as a result, you cannot go too far with also in time with those computations. Here, they started at t=1 and they stopped after less than 5 dynamical timescales. But yeah, on the other hand, you see that the difference, this is the velocity, I think, or whatever, does not matter what it shows. Anyway, you see that the picture at 4.25 and the picture at 4.68, they already look more or less similar. While at the beginning, they assumed kind of random small perturbations. So of course they had to assume small magnetic field at the beginning, but it was quite randomly organized. And they got something which is sort of microscopic. So that shows that in the nonlinear regime, this turbulence saturates and the mechanism works. It should lead to stationary accretion flow with some corresponding viscosity. Oops. And now we enter into the difficult part. Because if you see such results like the one I showed before, you would like to ask the question, okay, so which alpha we should use, for example, in global time simulations? And there is really no good answer to this question. Some people doing very advanced time-dependent MHD simulations simply refuse to answer this question because they say that this is a stupid definition and they are not going to show that. Some people show that, but then there are some underlying assumptions. Because in the case of magnetic field MHD simulations, you have to rely on serious assumptions, and everything matters, including the grid. So it's very difficult really to find some claims of alpha simulations. But, well, here I found some examples. This is from Mahida and Matsumoto group. They calculated the average value of viscosity alpha, integrating over the disk radially, vertically over their simulation part, and they calculated alpha as just the ratio of b squared divided by 8 pi pressure. Well, this is the initial time when the simulation somehow got relaxed, and they got a value which is quite interesting, just below 0.1. More or less what we need from observations. That's quite interesting. This is a different plot. This is from Oleg Sandowski. This shows the same alpha viscosity, more or less defined like this, although they were more specific how they calculated. Now as a function of radius. This is interesting because it shows that viscosity somehow, at least in these simulations, is higher at small radius, and then it drops with the radius when we move outward. On the other hand, it's important that those simulations are global, but those simulations are 2D simulations. And as I know, but I don't understand, 2D simulations do not fully include the action of dynamo. So if you ask me how those people were able to calculate the viscosity when the dynamo action is not fully included, then my answer is I have no idea. So can anybody of you doing MHD tell me how you can include, how you can calculate the magnetic fields when you have 2D simulations and no fully described dynamo action? Okay, if not immediately, then if you know the answer to this question, please answer it after my lecture, because I don't understand. I don't know how it happened. But it does happen, yes. People do 2D MHD simulations and they get magnetic field. And they imitate dynamo, although it's not proper dynamo. And I would be happy to understand what is the difference. And in general, occasionally now people do global simulations, not just shearing box, because shearing box is really very, very limited. But rarely those 3D simulations are 3D. More frequently, they are 2D. And I do not quite feel what we miss if we use 2D, but certainly we miss something. If the dynamo is not working properly, we miss something. And in general, either it's 2D or 3D, there are two important things. We have to deal with boundary conditions in such simulations and with initial conditions. Boundary conditions are simple because that is always present. If, for example, I imagine just time-dependent computations of the accretion flow without magnetic field, if I have some time-dependent instability, so everything inside the disk depends on time, still I have to tell global parameters, like, for example, black hole mass, external accretion rate, which is coming from the companion star. That's the boundary condition. If it is stationary, then I can follow this kind of saturated time evolution, and at some point the behavior of the disk does not have to be static, but it's kind of stationary. And in this case, for example, if you start with certain surface density profile inside a disk, after some time, it does not matter. The starting point did not matter. What matters is the black hole mass and the inflow external accretion rate. And the flow will relax to either stationary or non-stationary time-dependent evolution, but it will relax to something which does not depend on the initial density as a function of radius. On the other hand, even in computations of time-dependent accretion disks, sometimes the initial values matter, and the stationary solution is never achieved. Because, for example, when we discuss the tidal disruption event, right, you had black hole mass, that's easy, but you also have to put your material there at some radius, R0, and then everything will depend on this radius. The time evolution, the time scale of the diffusion of the matter will depend on this setup. So in that case also, you have this explicit dependence not only on boundary conditions, but also on initial conditions. In the case of MHD simulations, you always have dependence both on external boundary conditions and initial conditions. And the dependence on initial conditions is very, very important, because in most of those simulations, they do not supply the magnetic field. They frequently do not supply the mass either. They start with some configuration like a ring, like in TDE more or less. And then they follow this kind of evolution till the thing dies. And of course, you have always to remember that if the magnetic field is initially 0, it will remain 0. So whatever seed magnetic field you put in, you will get out. Of course, it will be modified somehow by the action of Dynamo, but it will really depend on the fact whether you assume some global magnetic field or not. If this global magnetic field is of poloidal geometry or toroidal geometry or whatever you assume will remain there. Right.
So when you say that those simulations are 2D, so this Sadowski 2D or it was 2.5D?
Well, those simulations, I mean, this is 2D, which
or
means
is it 2.5? Because they won't report if it's 2.5. They will say it's 2D. And also, I think
I don't know.
Does it depend on
as I said, I never did those computations myself. So if I read the paper, I'm not sure what happened. But I assumed they take into account axial symmetry.
Yeah, so it's axial symmetry. Okay.
So in this sense, it's 2D. So I'm not sure how this. So there is probably some hidden assumption which mimics what is happening in phi direction, but that's a tricky part, right? So it's better to have 3D, but it's okay. It's expensive, right? You need to have a lot of money to do it. So you have to pay attention to this fact that this initial assumption about the magnetic field is important. And sometimes when I read the paper, well, it's not important, whatever we assume, and then the magnetic field does miracles, whatever. This really reminds me things which, when I was a child, I had this book, Adventures of Baron Münchhausen. It's a kind of interesting story. I'm not sure if you are familiar with this story. Maybe not. It's more popular in European culture anyway, and then it used to be more popular in the past. I think it's partially forgotten. But the story goes that, well, this guy, Baron Münchhausen, he had a lot of different really impossible adventures, and the most notable adventure is that when he and his horse, they found themselves in the mud and just drowning. Then he started to pull his hair, and with this effort, he got himself and his horse out from this mud. So this is the key achievement of the guy. Actually, the story is said to be, it was written, 2 centuries ago. The stories are partially based on a real baron who was going around and telling what kind of adventures he had in Russia and, Siberia, whatever. Probably he was never there or something like that. So, but stories are very nice. And this is, I think, really illustrating that, this is not possible. So if somebody tells you that he didn't put any magnetic field and still something happened, you have to check what really happened or whether he really got the result. Always remember about this idea of pulling yourself out by pulling your hair. And this is short illustration of difficulties in really reading and believing into what people report to you if you are not an expert in MHD simulations. I was very much interested in this radiation pressure instability. We wrote a number of papers using alpha viscosity. Now, with this magnetorotational instability, we have physical mechanism. So we shouldn't be guessing if this instability is operational or not. We should be running MHD simulations and we should see, is it working or not? But this is the report of the answers. Well, in 2004, Turner claimed that disks dominated by radiation pressure are stable. Now, a few years later, Hirose, Bless, and Krolik confirmed that there is no thermal instability in their better MHD simulations, although they said that maybe they see some traces of viscous instability, maybe. But no thermal instability, absolutely no thermal instability. Then a group by Zhang, if I pronounce him correctly, who actually included some of those authors, they published MHD simulations where they saw radiation pressure instability. So between that paper and that paper, they slightly changed the code from Zeus to Athena, which shows that, that women are doing better. And I think they changed the grid as well. Then there was one more paper. I didn't list all the papers. They claim that disks are finally stable if the magnetic field is not too strong. And then the same group, 5 years later, published a new paper, and they finally said that there is no radiation pressure instability. So honestly, what can I say? Which of those papers should I believe, and should I change my view on radiation pressure instability every 2 years? So in each case, it would be really necessary to trace precisely what they did. And it's difficult, and because I'm not an expert in this field, I cannot easily catch their heads.
Yeah, but now whatever is the answer, Jack will be cited because he obtained both. So.
Yeah, sure. Good point.
But then Jiang average.
Then another a bit frustrating thing is with jets, although that I think looks a bit better than this issue of radiation pressure instability, because you know, we'll talk more about jets during the next lecture, but I wanted to briefly mention that if you do 3D MHD, you should see if you produce a jet or you don't produce a jet, right? So do we see a jet in 3D simulations? So this, I used only the most recent examples because there is a progress in those 3D simulations, so the most recent things. So this is a paper published this year. There is something like outflow here in the form of a jet. They mostly see winds. What they see is quite interesting about the inflow. Here they have an accretion flow. Here they have an accretion flow, but in the intermediate period, they have the situation when the accretion flow got stopped, and that looks like magnetically arrested disks, which are sometimes postulated. It's, I think, quite convenient, maybe for some observational aspects. Anyway, those disks are quite hot, by the way. This is never a Keplerian cold accretion disk. This is a hot flowing plasma. But as for those jets, here they show clearly that this is the positive velocity, negative velocity, so you have outflow in this jet region. But then if you look at the Lorentz factor between 0 and 200 gravitational radii, then this Lorentz factor at most approaches 2. This is not a relativistic jet. 2 is really nothing. To explain observed jets, we need 10 or 20. So it's not accelerated, at least in those simulations. And then it's really important to notice, as I told you, those simulations are never global in the sense like they are never stationary. They start with some initial setup ring, and then they end when the ring is empty. This is the mass in the time domain as a function of time. So they stopped computation when the amount of mass dropped below 20% of the initial mass. They just empty the zone. They don't know how to supply the magnetic field. That's probably the reason, because to supply mass to the grid is easy, but to supply magnetic field is not. So they prefer not to touch anything. This is another simulation, also this year, but this is 2D. I'm not sure if this is a problem or it is not a problem. On the other hand, it's quite advanced. It's GR, MHD GR means general relativity. So here they have much thicker accretion flow somehow, and then the jet forms. And what we can see here, indeed, they follow the jet up to much larger distance. Actually, you see here the Lorentz factor plotted as a function of radius up to 10 to 5 gravitational radii. So you see that there is no jet here, but you see finally the formation of an acceleration of the jet more or less at 1000 gravitational radii. Well, the jet is never very, relativistic, but a factor of few, well, they can achieve 10 is here. On the other hand, the solution is quite smooth here. I told you that for discussion of X-ray binaries, we need compact X-ray corona. You do not see anything like compact X-ray corona here. And this is never seen in any simulations. On the other hand, they discuss some issue of pinch instabilities, but I'm not sure if this pinch instability can happen earlier. Probably not. Probably this is only visible at larger distances, and then it can be related to dissipation in the jet. Oops. And in that paper, they did something which is rarely done in MHD simulations. I think this is the only paper, at least it is the only paper I found, which contains simulations and some observational data, because in most cases, people doing MHD simulations carefully avoid even giving alpha viscosity, not mentioning the comparison with anything, even remotely available from observational data. Here, they use the measurement of the disk thickness, or as they call disk radius, as a function of distance. And this is, so those blue pots are coming from a number of different papers, and it is for this object M87, which was really recently studied. And well, they are quite happy that one of the simulations follow more or less the size, so the level of the collimation of the jet. So that's interesting. On the other hand, indeed, we have to remember that those are simulations done for the hot flow kind of ADAF, and then, of course, applying it to N87 is justified, because this is an example of hot flow. It's not called Keplerian disk. It's low accretion rate source. And this is this last paper I mentioned already, where they claim that they do not see radiation pressure instability. So they do 3D, if I understand correctly, but well, as usually in such complex computations, they have only two examples, two solutions, and they were using an incredible amount of computing time and some million CPUs for half a year or something like that, you know. Well, in US, they have some possibilities like this. They had really a special grant to do that. And they were able to calculate accretion disks, which are almost like standard disks, so sort of Keplerian, but magnetized. And so they assumed certain initial configuration, and later they looked how much accretion they get out from this configuration. I think this low Eddington ratio case contained one magnetic loop, and I think this 20% started with two magnetic loops. Don't ask me how they were organized. So with two magnetic loops, the turbulence was more efficient, and then accretion rate was higher. However, what indeed they see, and what is quite new and important, is that they see some significant stratification of the flow. So part of the flow indeed proceeds, something like half of the flow proceeds through the thin, geometrically thin flow. This is really new, and this is difficult to achieve and to resolve in MHD simulations. This is an advantage and achievement of this paper. And then more or less half of the flow forms a kind of coronal flow. I like that picture very much, because I think we need this kind of inflow as well. On the other hand, they do not have something like hot corona. Their corona, this is this warm corona, the temperature is more or less 10 to 8, never 10 to 9, never compact. So then they don't have compact corona. They have kind of warm corona, which we also see in the data. So I'm quite happy with that. The problem is what happened with hot corona, why we miss that. And then in this case, you see only inflow and not outflow. This is because of the configuration of the magnetic field. probably, which prevents jet formation. You see here, even here, you have inflow. Outflow kind of wind you see here from at larger distances. Still, it's difficult to calculate more example because it's really incredibly computer consuming. And they say that, well, this source should in principle show radiation pressure instability, but it does not. On the other hand, they plot here some quantities, and I wouldn't call this really stationary. I think they see traces of radiation pressure instability, only they do not admit that in the paper. I didn't show here the plot for 7%. 7% looks kind of smooth with respect to stratification. This is time, this is, for example, the density. That looks like nothing is happening, like stationary. Here they see some kind of bumps with this thin disk getting denser and less dense, denser and less dense. But of course, they couldn't continue longer with this kind of thing. I think it's really more interesting, this simulation that the authors actually admit. So I'm not saying that nothing can come out from MHD simulations, but you have to be really very careful. You have to check what people tell you. And of course, there is some future in this, because we cannot solve this kind of problems fully analytically. And this kind of pulsation in the form of forming warm corona and then suppressing warm corona, because here it looks like more warm corona than less warm corona. That's quite interesting in the context even of observational data. And then to finish the today lecture, I will tell you something which I do not completely understand. Many people, particularly Russians, who are solving a lot of things with magnetic field analytically, they will tell you that if you have small scale magnetic field, you will never create large scale magnetic field out of that. Miracles do not happen. On the other hand, we know one observational case where the miracle does happen, and where people say they can model it. And this is the case of the sun. I do not understand it completely, but I will just report to you this. So, sun rotates always in one direction, right? Nobody questions that. Sun has solar cycle, very regular solar cycle. Here you see the years, so the plot started in the 400 years ago. You see Maunder minimum, then the number of sunspots. This plot shows the number of sunspots. It was recently increasing, now it's again decreasing. The last sunspot, the last maximum was quite slow, faint. Now we are in the solar minimum, waiting for the next peak, which is predicted to be faint. There are still discussions whether this is related with the climate changes or not. This is the small ice epoch period. We don't know. Anyway, why it is interesting? If you look what happens during the solar cycle to the magnetic field, it shows you that every 11 years, the global magnetic field reverses the direction. First, you have the North Pole and South Pole, and then you flip, and then you have South Pole and North Pole. Global magnetic field of the sun changes direction every 11 years, despite the fact that rotation of the sun is always in the same direction. I cannot imagine that sun starts to rotate in the opposite direction, right? So there is a global field which reappears out of nothing, all of a sudden, with opposite directions. The same happens actually in the case of Earth, but then the situation is irregular. The changes happen unexpectedly, totally unexpectedly, so it's even worse. So there are people who actually try to account for this, and there are numerical or even semi-analytical solutions which show that it does happen. Somehow it flips. So those people calculated this is a simulation of solar cycle by Strugarek that was published in Science, I think, in 2017. So they can reproduce this even numerically, only I do not understand how it works. If it is reproduced analytically, then people say that you have two excitation modes, and those two excitation modes interact, and this interaction leads to this flipping. Don't ask me how it works. So you can see examples of this kind of flipping. Usually you see some picture like that, and then if I look at this picture and I look at this picture and I see differential rotation, I see that the magnetic field, which is initially polar, multiplies, but then how it reconstructs with the opposite direction, I really don't know. So this picture, or many such pictures which are internet, to me, they do not explain the flip. Of course, rotation is important, but then you create some kind of chaotic, strong magnetic field through this rotation. And this field is indeed quite strong. At the lower layer of the convective zone, this magnetic field has the strength of more or less 1000 Gauss. And then you see this magnetic field in solar sunspots, because then you look deeper somehow, or this magnetic loop emerges. And then somehow, out of that mass, something emerges which is large scale, but of course 1000 times of lower intensity. So apparently it is expensive. So you have to generate turbulent magnetic field 1000 times stronger in order to produce something which is global. But somehow it's possible. And then somehow some people claim they can model it. Not in the context of AGN. Nobody tried to create a global global magnetic field of the disk in context of accreting sources. But in principle, perhaps it can work. I don't know. Or maybe those people who claim they calculated everything properly, they cheated. I don't know that either. So this is the summary of the lecture. I hope you agree and you understood that magnetic field is important. So learn magnetic field. But there is a gap between simulations and data. From the data you have spectra, power spectra. People doing MHD, they never produce any radiation spectra, any power spectra, just not to show that it does not fit the data yet. On the other hand, progress in numerical computations is really enormous. I'm not sure which one is really crucial to get finally something which is looking like what we see in the data. But some people already do GRR, 3D MHD. This is the most advanced version, which means general relativity, radiative, 3D MHD. So that's probably the future with computers improving. But if you look at any publications and you see a claim that something is possible or something is impossible, first to check what are the underlying assumptions. I mean, initial setup, etc. And there is no homework unless somebody volunteers to explain me how the solar cycle works. Thank you. Questions? Comments from those who are doing MHD simulations? I never touched anything. Never, because I'm scared.
Yes, I can say that most of the 2D, they are actually 2.5D. That means they include the 3D magnetic field, but the domain is 2D. The calculation domain is 2D. So
what is this half of the dimension doing? So, can you explain somehow in a simpler way?
So you evolve all the equations, but like you don't evolve the phi direction, but the phi terms are there in the other two equations.
But then if the turbulence is actually 3D.
Yeah, so I actually do 3D, so I am not able to comment. I mean, I find turbulence also, and I don't know what my simulations are like giving a surprise. I actually find the results that from a small scale, it actually goes to large scale. And the reason we are trying to explain it is that it has to do something with the magnetic helicity and its conservation, which drives an inverse cascade.
But your magnetic field only multiplies or it decays due to magnetic field reconnection. That's another thing which always won't.
Yeah, which is I'm not sure about the magnetic field reconnection. I think we have
because some codes do that numerically in a sense. If you don't even do anything, then numerically your magnetic field decays. Am I right or not?
Yeah, I mean,
like numerical viscosity, that's the same thing. Sort of. So then sometimes things depend on the grid. Check also the grid because if you have smaller grid, then the decay will be faster, right? Good guess, but I'm not sure. Questions? Okay, experts are depressed by my lack of knowledge, and everybody else is depressed by the difficulties of MHD, right? Okay, thank you.